All right, welcome to the final lecture of the class. All right, so to remind you where we are, we're in chapter 13. A kind of an introduction to partial differential equations, a survey of some of the different areas in the subject. Okay, so we covered the heat equation in the last lecture, equation that the temperature of points in space, well, on a, we just considered one-dimensional situation, but must obey over time. Okay, so now let's, there's going to be two more partial differential equations we'll study in depth. The first of which we'll cover today is the wave equation. Okay, so the physical setup for this is the following. You have imagine you have a plane here, and this is the x-axis, and you have some string that is tied down on either end, but it may be vibrating. So, imagine a string, like a string instrument, or like a relatively tightly strung jump rope or something like that, where the impact of gravity is negligent. So it's the tension is deciding the physics more so than gravity. The force from tension is much greater than the force of gravity on a small little portion of the string. Anyway, so that's the setup, tied down at either end. And what we want to model is the displacement. This little height, the height off of the x-axis that the string is vibrating up and down. Okay, so here is the equation that it will satisfy over time. So you imagine at time t equals 0, here is point L on the x-axis, and you have some string, and the graph of this function, this is a string, and you imagine a function whose value at some point x is the distance from the x-axis that the string lies at that point. Okay, so this would look like the graph of u of x comma 0. This would be the picture at time t equals 0, and then at some short time later you get a different picture. You could graph the function u of x comma 1 second later, and then maybe it looks slightly different. Still attached at the two ends, but it maybe looks, so it's still height value 0, height 0 at either end, but it may look like some different function of one variable. And you kind of get a movie as time changes of the string looking different at different times. Okay, so there's a derivation. This comes from physical laws that you can work it out from basic properties of how tension works. But the upshot is that this is the equation that u, the displacement of a tiny portion of the string off of the x-axis, will satisfy if you just take into consideration the tension of the string. No gravity, just tension. Okay, so what does it say? It says that, okay, we have a function of two variables. You plug in some number x between 0 and L, and then some time that's bigger than 0. And then you get a number which represents the sign displacement, because it could go above or below, sign displacement from the x-axis. So it's vibrating in 2 dimensions. It's a one-dimensional object because it's just a string, but it's vibrating in 2 dimensions. Okay, just to, if you might not be so surprised to find that, or to learn that, where does this equation come from? Well, it is, as usual, for all of our mechanical problems that we've talked about in this class, it all comes from forces, mass times acceleration. Here on the left-hand side, we see something like acceleration. That's the acceleration of, say, a tiny point on a tiny segment of the string. And then if you zoom in close to this point on to a tiny point on the string, you get a picture like this. This is the tiny point that lies above X on the X-axis. And you can take a look here and you can analyze, okay, there's, just to give you a sketch of what's going on here. You analyze, okay, there's some tension because the fact that the string is attached, on the left. You think of the string as made up of many tiny segments that you take the length of going to 0. In any case, so you have from tension, you have some force acting in the left direction, some force acting in the right direction. They have to do with the derivative, the x derivative of u at that point. You have these two forces in opposite directions that come from the tension. And then, then there is the acceleration over time, two time derivatives. It's equal to, some force in that direction, some force in that direction. They don't totally cancel out, otherwise there wouldn't be anything interesting happening. But anyways, you kind of get the difference of two derivatives taken at slightly different points. They don't totally cancel out because I'm not taking the tangents at the same point. I'm taking them slightly off from one another. Anyways, you take their difference and then you divide by the length of any line segments. That gives you, because each of the forces has to do with the derivative, and the difference divided by a small number of those forces looks like time derivative, or is it two time derivatives? Because it's like they're already x derivatives, they're already x derivatives, and then you're taking the difference of two of them divided by a tiny length. That gives you a second derivative. Anyway, so that's why force equals mass times acceleration gives you an equation like this. Two time derivatives is proportional to two x derivatives. This is the wave equation. The C is some number that depends on the material. Okay, so this is a very different equation. It looks a little bit like the heat equation, just to remind you, the heat equation. That just looks like a one-time derivative of u equals, some number k times two x derivatives of u. Okay, it might seem like an innocuous difference, but it behaves wildly differently than the heat equation, and we'll see that very soon. Okay, good. All right, so let's start taking our first forays here. Okay, so let's figure out what is the correct initial value problem. What are the boundary values that we need to impose in order to get a unique solution to the equation? Okay, so first of all, we've already said what should be happening at the endpoints. We've nailed down, our string is attached at two endpoints. It doesn't need to be, by the way. You could consider other boundary conditions, but these are the most basic ones. These are, Dirichlet boundary conditions. Okay, so that kind of that's two conditions in the x direction. Those are two kind of x related conditions, and there's two x derivatives. So that kind of check mark on that. We kind of took care of those two x derivatives. Remember, we're kind of counting the number of derivatives that we see, and we should have some initial condition for each of them. Okay, so we kind of have initial conditions that should take care of those two x derivatives in the sense that they should determine the two constants that come from integrating those two x derivatives. In theory, not really. This is not explicitly what we do to solve the equation. We don't just integrate, but that's the rough outline of trying to nail down a specific solution to the equation. But then we get these two time derivatives. So you expect two initial conditions that need to be imposed. Unlike in the heat equation, there was really only one initial condition that needed to be imposed. Here we should expect two because we have two time derivatives there. And in theory, in solving for u, you're integrating with respect to t twice, so we should need two initial conditions there. Okay, so the two initial conditions that are natural to impose in this context is one, the initial configuration of the initial displacement of the string. You know, the picture of the string at time t equals 0. You know, you could imagine, for instance, you are kind of like, this is your hand here, and you are just plucking this string up in the middle, say. That would be like an initial condition. The initial condition would be, you know, it looks like some linear function here and then some linear function after, you know, midway through, say. This would be L. And the height at any given point would be, you know, u of x at time 0. And so that's described by a function of x. So a function of x describes the initial displacement or initial configuration of the string that you're going to require. But that should not be enough to determine how the solution should look over time. We should also impose another condition represented by the initial velocity of each point on the string. You know, at this point, is the spring going upwards or downwards? This is described by another function, g. This is like initial velocity. Of this string. Okay, because you could imagine, you know, the string being plucked up like this, that could result, you know, you could be lowering it down and letting go, or you could be lifting it up and letting it go. Those would give you two different sounds, two different vibrations. Okay, so the point is, if we're going to decide on these Dirichlet boundary conditions where we have the two endpoints of the string nailed down, then there's two pieces of initial conditions that we need to supply, which are two functions of x. I call them f and g here, the initial displacement and the initial velocity. Okay, so let us try to solve the wave equation. So we're trying to solve the equation partial t of u equals c squared partial t or partial x of u. Okay, so what should we do if we want to solve it? Well, our new favorite thing to do, you know, the thing that we did for the heat equation, is to consider separation of variables. You say, okay, suppose our function can be separated as the product of two functions, one of just the spatial variable x, the other of just the time variable t. Suppose that u takes that form, justified later by a Fourier series. But suppose u takes that form, we'll see what we get, and then we'll try to formulate a solution to the wave equation. Now, this is going to be a little bit different for the wave equation. This will give us a solution. We'll be able to write down a solution, but it won't necessarily be transparent what's going on. Just to give a little bit of a spoiler, the limit as the limit as t goes to infinity of u of xt is not going to settle down. It won't exist. It won't exist unless you're constant 0. So unlike, you know, how we saw for the heat equation, over time heat dispersed evenly throughout the room, or, you know, about the metal rod. We were just thinking about a rod placed on the x-axis from 0 to L, and we found that the solution to the heat equation, as t went to infinity, it converged to just a linear function that interpolated between the two boundary conditions, because the heat is trying to be as evenly distributed as possible, and that is what it does. That's what heat does. That's not what waves do. That's not what you know, like a string does in the absence of, you know, gravity and friction and stuff like that. If there were no gravity and friction and you plucked a string, it would vibrate forever. So, which is to say that, you know, it's going to be oscillating. The function u of xt will be oscillating in t. It won't ever settle down. Okay, so things are going to be quite different here. Okay, so I mean, so that's we'll come up with some formulas that won't necessarily reflect. Well, we'll look at two perspectives on solving the wave equation. Okay, so here's the first one from the technique we learned for the heat equation, separation of variables. Okay, so suppose u takes the form product of x stuff and function only of t. So then we write down, okay, partial t of x, of u. Well, that is just x times t double prime, and c times partial, or c squared times partial x of u is c squared tx double prime. Now these two things need to be equal by the heat equation. That's what the heat equation says, that those two things are equal. And so that tells you that xt double prime is equal to c squared tx double prime. And so you just divide by the appropriate stuff. You get t double prime divided by c squared t is equal to x double prime divided by x, which is what we just claimed. Okay, so we assume that there is a separated form for the solution, and then we just rewrote the heat equation and we separated, you put all the x stuff on one side, all the t stuff on the other side. Okay, so this is a precarious position like we saw in the heat equation. The left-hand side only depends, it's only x function. And then the right-hand side is only t function. And the only way for two functions that depend on two different variables to be equal is if they are just constant and the same constant. So suppose they're both, so I mean, they are constant, and call that constant minus lambda. So x double prime over x is equal to minus lambda, and t double prime over c squared t is equal to minus lambda. And multiplying both sides by, x or c squared t, that tells you these two equations. So x double prime needs to be equal to minus lambda x. And for that same lambda, t double prime needs to be equal to minus lambda c squared t. Okay, that's all we know so far. Oh, and by the way, also, our x is representing the x part of the solution. So it needs to be 0 at the endpoints. Also, x at 0 should be 0, and x of L should be 0. Okay, so that's what we know so far. Now let's try to solve each of the equations. So let's inspect the x one first. And we'll be able to kind of solve that pretty concretely. And then that will tell us what lambda is, and then we'll approach the t equation, and then put them together, multiply them together to get a solution to the wave equation, and use that as our building blocks for the solution, for a general solution to the wave equation. That's the strategy. Okay, so just like the heat equation, except the equations are slightly different. For the heat equation, this t was much more simple. It was just first order, but here it's second order. So quite different. We'll see how that affects things. Okay. So first, let's see what's going on with x. And this is actually exactly the same problem that we saw for the heat equation. So, as by before, I mean for the heat equation. So make sure you take a look at that lecture or that section. But anyway, so in there, we solved that part. We solved the problem x double prime is equal to minus lambda x, and x of 0 equals x of L equals 0. So just to remind you how that worked, first we found out that lambda had to be positive. not unless we're looking at the zero function, but if it's not zero, then there's no solutions to this equation. So if x is not zero, then there's no solution to this equation for lambda negative. Okay, you can see that by integration by parts, or you can see that by just seeing that if lambda is negative, then you get exponential function solutions, and you're never going to achieve zero conditions at two different points for the sum of two exponential functions. Anyway, so right, the idea is, okay, you first discover lambda has to be non-negative, and then you have sine and cosine solutions. The eigenvalues are pure imaginary. You get sine and cosine functions solving the equation. The fact that x at 0 has to be 0 tells you there's no cosine part, so the constant. So the function just has the solution x has to just be a sine function, because cosine of 0 is always non-zero. So if you require it, that'd be 0 there, then there can't be any cosine. And then the fact that when you plug in L to the function, you get 0. That tells you that the lambda can't be any number, because just to remind you. Well, we already went over this, so maybe let me not belabor the point. We find that lambda has to be the square of n pi over L, and that the solution itself has to be perhaps a constant times sine of n by x over L. Okay, so just a simple sine function. So, just to be extra clear, x just looks like some sine function, starts at 0, ends at 0, and it's perhaps very wiggly. An unlimited number of wiggles determined by the size of n. Anyways, this works out for any whole number of n. Okay. Now that we know what lambda is, we know it's positive, and all that. Now we can approach solving for t double prime. Or sorry, solving for t, knowing that t double prime is equal to this. And let's not worry about initial conditions. Yeah, so as I say here, without any attention to initial conditions, we worry about that later. But just like for the heat equation, we didn't worry about the t initial conditions at first. We found an appropriate combination of solutions that would give us the correct t initial conditions, and we'll do the same thing here. But anyway, so we know that t solves this equation. So that tells us that t is equal to just the linear combination of these two sine and cosine functions, because remember, we know what lambda is. Lambda is, or rather, the square root of lambda is n pi over L. So we just put that in, and also we know we got that c there, so we got that c there. So we know that t is equal to just some constant this plus some other constant times the sine function. Okay, just solving a simple looking linear second order equation. Not a big deal. We've done this many times. Okay, good. So now let's put things together. We get these two building block solutions. So we have it's x times t, where we just figured out that x was going to be some constant times sine of n pi x over L, and we just found out that t is some constant times cosine cn pi t over L plus sine cn pi t over L. Okay, so I just wrote that as two different building block functions. The un, which is the cosine in the t part, so that's sine of n pi x over L times cosine cn pi t over L. And the vn will be the sine x function times the sine part of the time function. Look at these two basic building block solutions. There's a lot of numbers floating around here. The c, n, and the pi, and the L. But just try and tune that out a little bit. The point is, you get that one sine function of x multiplied by these two different trig functions in t. Okay, those are our building block solutions. They form, as we know, by what we learned about Fourier series. These will be a complete set of solutions to the wave equation. And so, in fact, any solution to the wave equation can be written as a linear combination of these two functions. So I'll just write that as an infinite sum. Why not? So long as it converges, that's a fine thing to say. Infinite. Well, what you really need, this to really make this precise. You should. This is valid for any, for any sequence of an and bn, so that the sum of an squared and the sum of bn squared are finite. But that's a technicality. Don't worry about that. That's just an aside. If that is satisfied, then this will be a genuine solution. But the headline is any linear combination of these two building block solutions will be a solution to the wave equation. That's why I said this wouldn't be all that useful, because it's not so clear what this looks like. But the basic picture is like a product of a sine function of x times say a sine or cosine function of t. That's the basic energy that's the basic thing that's happening with these functions, with the wave equation. So like a typical solution to the wave equation would look something like, say, u of xt. So let me just give you an idea of what we're looking at here, what kind of territory we're entering into. So one of the basic solutions, say like all of the bn's are 0 and like all of the an's are 0 except like a6 or something, or how about a4? So then it would just look like sine of 4 pi x over L times cosine of, so let's just say that c is 1. I'll often just assume that to make things a little more simple. 1 second. Okay, so we're looking at cosine of 4 pi x over L. Or sorry, t. Let me erase that. I can do a little bit better job there. Cosine of 4 pi t over L. So it's typical, just to set your expectations for what's going on. So let's see, what does this look like? So this looks like a sine function in x. So let's try to draw the movie. For each value of t, we'll get a different function which represents the displacement of the string. And so let's try to, let's think about freezing t at different values. So then this solution will look like a sine function, which is scaled by cosine of t, roughly. Scaled. It's not how you spell scaled, but let's ignore that. Scaled by cosine of t. We're speaking in very rough terms. So at t equals 0, what is the picture? Well, here is, say L is 1. So then the curve that represents the displacement of the string. So literally, I'm drawing what the string will look like. It will look like something like that. Yeah, it should go through 2 periods, so I do it going through 2 periods. Okay, so that's what it looks like if t is equal to 0, and well, t equals some later time. Well, let's see. 1/8, I guess. How about 1/16? And cosine will be like somewhere in between 1 and 0. So it'll be some positive scaling. So it'll be like it's like the sine function, but you've kind of dampened it a little bit. And then let's go later time, t equals an eighth. I believe at that point, it will just look like flat. And then at a later time, t is equal to like, well, let me, just at a later time. I don't want to do all these calculations in my head. So it's like the sine wave has been collapsed, and then I'm going to be multiplying it by negative numbers. So what used to be +1 now goes to -1. So it'll look like this. And then, some later time, it'll be damped again and go back down to 0, slightly damped, look like that. And then it will go back down to 0, and then it will repeat itself. So it's like a sine function that you're just multiplying by 1, and then it goes, then you start multiplying by negative numbers. And so it's just like it's a sine function that goes up and then goes to 0, and then it kind of continues in the opposite direction, and then goes to 0, and then goes up again. And it repeats that pattern forever and ever. It doesn't look too much like a wave, but it's a basic model for, these are supposed to just be the building blocks. Kind of like the harmonics of a musical instrument. The real noises that you hear are made up of these basic building blocks. So each one of these doesn't really look like that accurate of a model for what like the violin string looks like. You imagine the violin string is like much more evenly distributed, but it's the sum, it's the displacement that represents the function whose value represents the displacement of the violin string is made up of a bunch of sums of these basic building block functions, like we've just explained here. Okay, good. And you can, well, let's not go there. You can pluck a string instrument in such a way so that it looks like these very simple solutions as possible. Okay, but you have to do it in just the right perfect way. This is only one solution for just one very particular set of initial conditions. And if you change the initial conditions, then the whole wave looks different. Anyways, so this is a picture for, and these are solutions. Some of the general solution will look like this. Let me just factor out that sine, the x sine function out of the two. It will look like this. I just rewrote the same thing up here, except I just wrote out what u and v were. Okay, so now let's see how do we get the initial conditions to be satisfied. We got the x, the boundary conditions, the x conditions. It's going to be 0 when x is 0 or L. You just notice what's going on with the sine function there, and you plug in 0, sine is 0, that makes the whole function 0 when x is 0, same thing when x is L. But what about the t conditions? We need to impose, so we still need x comma 0 to be some given function f of x, and we need the x derivative of u at time 0 to be the given function g. The two pieces of initial conditions that are supposed to determine what the function is. And that's good news because we have kind of two parts of the function that are not determined yet, the a coefficients and the b coefficients. And you may not be surprised to learn those are going to be the Fourier coefficients for f and g. So that's exactly what happens. If you take this and you plug in, you just take this expression for u, and then you plug in t equals 0. What happens? Well, all the sine stuff goes. Yeah, sorry, this should be a cosine. Sorry. Is that right? Oh, sorry, I confused myself. This was correct. So if you plug in t equals 0, then all the cosine stuff is just equal to 1. And then all the sine stuff is just equal to 0. This is when t is equal to 0. That's what happens. And so you just look at the x stuff. And the x stuff is just sine. of n pi x over L. So this is what you get when you plug in 0 in for t. Right, you just get an sine n pi x over L. Now, on the other hand, if you take a derivative with respect to x of u, what do you get? Well, you get the sum of a bunch of stuff, sine n pi x over L. Then you get the an times the derivative of the cosine stuff. Now we're taking, we're taking t derivatives, t derivatives. Before I should have, this should have been a t, my mistake, sorry. Times, so it's an times the derivative of the sine, the derivative of cosine, which becomes a sine. So that's sine stuff. And then, but we're going to evaluate it at 0, so the sine stuff will go away when t is 0. And then you're just left with the bn times, cn pi over L cosine of cn pi t over L. And then when you evaluate that at 0, you just get that coefficient, just the bn times the cn pi over L times the sine function, the x sine function. Okay. Kind of it's confusing to look at now, but that's what you get just when you take the t derivative and plug in 0 in for t. So you get, and so these are almost explicitly just the Fourier coefficients, Fourier series for f and g. There's a little bit of weirdness going on here. First bit of weirdness is that, this is, we've multiplied by an extra number here, the cn pi over L, because we took the derivative. So that's a number that you wouldn't expect to see in the Fourier series for g. So when we compute what bn is, we need to take that into consideration. And then also, instead of going from minus L to L, as we usually did in the Fourier series, we're just going from 0 to L. That requires us to multiply by 2. And so, when we're trying to figure out what the coefficients are, and this is what the coefficients turn out to be. The ANs will just be 2 over L times integral from 0 to L of f integrated against the sine function, n pi x over L. Just the usual Fourier coefficients. But because of what the interval is, you have to multiply by 2. So it's 2 times what it would usually look like, but it's just the Fourier coefficients. Neither of these functions have cosine components because of the fact that they're going to be 0 at the endpoints for all time. You don't have boundary components. You don't have cosine parts of the Fourier series. Anyways, likewise, the bn is given by 2 over cn pi integral from 0 to L, the product of g and the sine function. So it's like a Fourier coefficient, except you've messed it up a little bit because of this cn pi over L. So really, cn pi over L times bn should be the Fourier coefficient. So that should be 2 over L integral from 0 to L g of x sine of n pi x over L dx. Not enough room for the dx. So that's what that should be. And then when you solve for bn, you get this formula. It looks a little slightly different. That's just because that comes from taking the derivative. Okay, so there you go. That is the solution to the wave equation. It's given by this sum of sine and cosine functions. Sine function in x, because we were requiring 0, it's nailed down at the 2 endpoints, so it just has to be a sine function. Can't have any cosine parts. And then in the temporal direction, the t stuff, that just looks like a sum of sine and cosine stuff, where the cosine comes from the initial displacement. The coefficients are just the Fourier series for the displacement initial condition. And the numbers next to the sine temporal part, you could say, are just given by an appropriate scaling of the Fourier coefficients for the initial velocity function. Okay. Kind of hard to imagine, it's hard to solve this, to write down solutions very explicitly and get a feel for them. But that's just what the separation of variables tells us solutions look like. And again, we are justified in making that separation assumption that U splits as a time thing times a x function. Okay, but that's not necessarily the main focus that I want to take here. Let's take another look. Okay, so this is the second approach, so-called D'Alembert's solution. Okay, so we're still trying to look at the wave equation. Let's just think. Let's think C is 1. It's not interesting to think about the C, but you can do everything that I'm about to say with the C there. Some C not equal to 1, but it might just confuse things. And let's just think of C is 1 for this discussion. The real content is just studying this equation. 2 time derivatives equals 2 space derivatives of x of U. Okay, so let's take a different perspective. We can do that generally for a lot of different partial differential equations. You can do the separation of variables thing, and it will give you a kind of formula for a solution, but mileage varies with it. It's not, it's a bit of a doozy, this formula, and it's not so clear what's going on. But this sort of approach, separation of variables, solving, writing down series solutions, figuring out what the coefficients are, you can do that for a lot of different equations. It's a very widely usable thing. But let's think about something that's specialized to the wave equation. That's what this D'Alembert solution is. It's treating the wave equation as a special thing. Okay, so instead of thinking about x and t, the usual, the space and the time coordinates, let's consider these different coordinates. So instead of thinking of the x and t, let's separate into 2 other things. It's called xi and eta, where xi is the sum of x and t, and eta is the difference, x minus t. So now let's, instead of thinking of time and space as kind of different, let's kind of jumble them up in this way. Instead of thinking about, I want to think about derivatives with respect to x and t, let's think, I want to think about derivatives in the direction of xi and eta. Okay, so let's try to rewrite it's like a change of variables, kind of like a U substitution or something like that. The equation will now look different because now we're introducing, the equation's, 2 time derivatives of U. Well, that's going to look kind of complicated at first glance in terms of xi and eta, because neither of them is just the next derivative. Just to be clear, so just note, partial xi of U is going to be partial x of U plus partial t of U. And partial eta of U is partial x of U plus or minus partial t of U. Okay. So you can think of it as a derivative with respect to a different coordinate. You can think of it as a directional derivative of this function of 2 variables in the direction of x plus t and x minus t. And by the way, x plus t, if this is x and this is t, then xi looks like this, eta looks like this, x plus t, x minus t. So it's kind of a coordinate system that is a rotated version of x and t. Anyway, here's what we have. Why is this a good thing? Well, let's see. Notice, note, let's take a partial xi and then partial eta u. Let's see what that looks like. So it's partial xi of Partial eta, that's a partial xu minus a partial tu. And then I got to do a similar thing here. So remember, partial xi is partial x plus partial t. So I want to do that on partial xu minus partial tu. What do we get? Well, this is a, you got to distribute. And what do we get? We get partial x u. And then we get a partial t, partial xu. So I've just hit those derivatives on the partial xu. Now I'll hit them on the partial tu. So I'll get a minus partial x, partial tu, and then a minus partial t, partial tu. And what happens? Whoa, we got a cancellation because derivatives commute. Partial t then partial x is the same as partial x then partial t for a function of two variables that's sufficiently smooth, which it will be potentially. Okay, so what do we get? We just get partial xu minus partial t, partial tu. Wow, that's a good thing because that is a lot like the, so if this thing equals 0, which is the wave equation, partial x u minus partial tu equals 0 is the same thing as the wave equation. So if that is equal to 0, then partial xi, partial eta u is 0, and vice versa. Much more simple way of writing the wave equation. Wave equation looks like it involves 4 derivatives, or if you introduce these coordinates, these wave coordinates or variables, it just looks like just like a xi derivative and an eta derivative of u has to be 0. Much more simple looking. It's not obvious that that was going to be the case, but it's a interesting thing to do. So it was good that we did that. Anyway, so the wave equation just becomes a much more simple looking thing. Take a derivative of u. If you think of u as a function of xi and eta now instead of x and t, which you can do because there's this law that allows you to, formula, definition that allows you to go from one to the other. Then the equation is very simple. It's just partial with respect to one of the variables, then do partial with respect to the other one. That equals 0. Very simple. What I say is very simple. You could integrate that. If you integrate with respect to eta, you get constant, and then you a constant with respect to xi, and then you integrate the resulting thing with respect to xi. Then you just get a let me tell you what happens. You just get, u just has to separate as the sum of 2 functions of xi and eta. It's very simple. I mean, it looks very nice. So, just integrate this with respect to eta, then partial xi u is just some constant with respect to eta, so it could depend on xi still. And then also you could write this as partial xi, partial eta of u equals 0. So that also tells you that partial eta of u is just a constant with respect to eta. So that's, or constant with respect to xi. So that's just a function of eta. Actually, let me reorganize myself. Let's write this in a different way. Yeah, just to match with how the book is doing things. Okay, you could integrate this with respect to eta, and you just get some constant with respect to eta, which could be still depending on xi, and then you integrate with respect to xi, and then u would be equal to the integral of h xi dxi plus some constant in xi, so it could still depend on eta. So call that g of eta. So then you could, if you call f the antiderivative of h, then this just looks like f of xi plus g of eta. So as I've written here. Okay. So if you just, just generally, if you have a function of 2 variables, so that if you take derivative with respect to one and then the other, you get 0, then it has to kind of separate as the sum of function of one variable plus function of the other variable. Not so surprising. Okay. So, wow, this looks a lot simple. We practically solved for it. We practically solved the heat equation very simply. It's just the sum, one function of xi plus another function of eta. And then if we unravel the change of coordinates, in xi and eta, we could just rewrite the u as a function of x and t. U has to look like, and we've done no boundary conditions at this point. That's the dicey thing. We've totally ignored any boundary conditions. That's the downside of this method. But we've solved the heat equation. This is what it looks like. It's just some function of f, some function f of one variable, but where you plug in x plus t. So it's just one function. It's a function of just one variable, but you're plugging in something that depends on two variables. But it's still just a function of one variable. And then plus another function of just one variable, you plug in x minus t to that. So as even if you're at the same point, as time is changing, you're plugging in different numbers to both these functions. Okay. So so let's take a look. We solved it. The f and the g, they don't need to do anything at all, aside from the boundary conditions that we've been totally ignoring. But if you totally ignore the boundary conditions, suppose this is an infinite string, so there's no boundary conditions, we've solved it. There's no conditions on f and g, just any functions of f and g. We'll solve the heat equation, or sorry, the wave equation. A lot better than the separation of variables, right? But we knew the boundary conditions are going to be a confusing point. But anyway, so let's see what the implications are. No conditions on f and g, they could be anything. And you will still get solution to the wave equation. Okay, so let's just test and see what happens. So we can take f to just be 0. Let's just do that. And then let's say g is a function that looks like a bump. Okay, so by that I mean something like this. The graph of g, I'll say it looks like it's 0 until like a half, and then it goes up to 1, and then it goes back down. And at like, I don't know, say this is a half, this is 1, this is like 3/2, say. It's just a bump that looks like that. And it takes that maximum value of 1. Suppose g looks like this. Just a function of one variable. Well, remember, we're not just going to be plugging in t or x into it. We're going to be plugging in the difference of x and t. Okay, anyway, so suppose this is what it looks, suppose this is what g looks like. G, and remember g was a function of what? Eta. G of eta looks like this. Okay, so let's see what happens. So this would be the picture when t is 0, right? If t is 0, then the solution just looks like g of x, which looks like this graph, this little bump. I've chosen what g is. I didn't write a formula for it. I just drew a picture of what it looks like. But I've supplied the g. And so the resulting solution, so this thing will solve, or just to be clear, this will solve the wave equation. If you take 2x derivatives minus 2t derivatives of that function, you'll get 0. Maybe let's do that just to make the lecture clear, just to reassure you if you're confused at all. So notice, let's take 2x derivatives, partial x of g. That will be, let's use the chain rule, that's g double prime. I mean, the chain rule is very simple because the derivative of x minus t with respect to x is just 1. So this is g double prime. And to see that, just note x minus t, partial t, or partial x, that's 0. And on the other hand, partial t of g, let's do that more carefully. Because remember, we're plugging in x minus t into g. So we take one time derivative, that's partial t of, g prime of x minus t, But you got to take the derivative of the inside function with respect to t, which is -1. So it's minus g prime. And then let's do it again. So it'll be minus the derivative of g prime with respect to t. That'll be g prime prime x minus t times the derivative of the inside function, which is again -1. So the -1's cancel, so we just get g prime prime x minus t. And that is equal to 2x derivatives. 2x derivatives equals 2 times time derivatives. Okay, so g of x minus t solves the equation. But just to be clear, if we verified that above, we derived that this would solve the equation, and indeed it does. For any function g, doesn't matter what g is. Could be anything. Anyway, so let's see what the implication is. It's been on the board for a while now, you may have read it, but this is going to look like just a traveling wave. Let's see what happens. So I drew the picture at time t equals 0. It's just a graph of g of eta. And when I plug in, say at some later time, 1, then I'll need to be graphing g of x minus 1 if I want to see what the wave looks like at time 1. So when you subtract 1 on the inside, if you remember how that affects how that transforms the graph of a function, if you subtract a number, a positive number from x on the inside of the function, like I'm doing here, there's the effect of shifting to the, well, it's been mirrored here on the video, but it shifts it in the positive x direction by 1 unit. It's not so hard to work out for yourself, but so instead of being centered at 1 there, now it's centered at 2. So it looks like a bump with a peak at 2. And then you're going to see what happens next. If t is, so it's supposed to be a 1. If t is, 2, I should have drawn it more uniformly, then the effect would be a little bit better. But it's not going to be at 1 or 2, it's going to be a peak at 3. And then, if I go on further, in time, it just looks like the wave is just translating to the right. That's what this equation predicts. That this will be a solution. This is a conceivable wave. This is a possible wave. Just a bump that is just slowly moving in one direction. If I chose g to be 0 and f to be this bump, then it would be moving in the other direction. I could have chosen them both to be this function, and then it would have looked like just two bumps that are moving away from each other at a constant speed just moving to the right. So there's some kind of like folklore story that when D'Alembert, discovered that these are, what the model predicts are, conceivable, physically reasonable waves, just a translating wave. It seems like an unnatural prediction, but so I guess the folklore is that scientific community thought this was a little bit nonsense, but you can actually see them. There are waves that exist for a very, very long time, even in the real world where there is gravity and other stuff. Waves that just look like this, just a translation of a bump in the water. Anyway, so this is certainly an interesting prediction, because that doesn't seem like something that a wave would necessarily want to do. But we've also not discussed the fact that this also applies to waves and fluids and stuff, and not just strings. But that's a separate discussion for perhaps another class. Anyway, this is the first implication that we see for the D'Alembert method, you could say. All right, now we've got to face the music, and we got this nice fact that if you just have two functions, you can write down a very simple looking solution to the wave equation, but these are totally on unbounded x scales, and we've imposed no boundary conditions. Now we got to impose the boundary conditions and see what happens. Okay, now let us And this is going to be a little bit unpleasant, but not that unpleasant, but it's going to be a little bit more confusing. Clarity in the formula for the solution is sacrificed in clarity and making the initial conditions work. So let's make it, even with that in mind, let's make an additional assumption. Let's assume that the initial velocity is 0 for the string or for the wave. And so there's going to be some f, which represents initial displacement. And let's not worry about the initial, I mean, you can do it, but it just gets more convoluted. Let's not worry about the initial velocity. Okay, so now let's do our thing. Let's impose the 0 Dirichlet conditions. So we're really trying to solve the full problem. Partial t, u equals partial x, u. Let's make c just 1 again for clarity's sake. We're going to impose Dirichlet boundary conditions. So the string is nailed down at 0 and L. So u of 0, t is equal to u of L, t is equal to 0 for all t. And u at x, 0 is some given function x representing initial displacement. And then partial t u at x, 0 is 0. Additional assumption just to make what I'm about to say less confusing. And the calculation is more simple. Okay, so right off the bat, we know that, so from this, we know u is going to be, x of t. It looks like some function x plus t plus another function of one variable where you plug in x minus t. Okay, that's the solution to the equation. Now, just to tell you what's going to happen next, I need to figure out f and g. These are just functions of one variable, but not any functions will do. Not any functions will solve the initial conditions. We need to figure out what these need to satisfy, what they need to look like. Figure out f and g, which satisfy the initial conditions. Okay, so let's start going through. So there's like 3 things to check. 1, 2, 3, or not to check, but to write down in terms of f and g. And let's just write down those 3 conditions in terms of f and g. Okay, so right, we know what the solution looks like. F of x plus t plus g of x minus t for any functions f and g. Let's see. Okay, so when I plug in 0 in for t, I better get f. So this is plug 0 in for t, you get this equation. F of x plus f of g is equal to little f of x, the initial displacement. Okay, simple. And taking the derivative with respect to time, partial t of f, well, okay, I'm just f of x plus t plus g of x minus t. That will be, okay, you got to do the chain rule. You take a derivative of f, so that's f prime at x plus t. And then when you take the derivative of the g, you got to multiply by minus 1 because you're taking the time derivative of the inside function, the x minus t, which is minus 1. So that's minus g of x plus t, or the derivative of g at x plus t, x minus t, sorry. It doesn't matter because you're going to be plugging in 0 in for t. So then evaluate at t equals 0. Then you get f prime minus g prime has to be 0. Okay, so these are the 2 time initial conditions. They tell you that. Okay, so in particular, f prime has to be equal to g prime. And so, they're just functions of one variable whose derivatives are the same, so they just have to differ by a constant. So f prime, sorry, just f itself, if you integrate, is going to be equal to g plus a constant. And that constant actually won't matter because f and g need to add up to be little f. So and, well, okay. Let me just tell you what's happening here. Okay, so f minus g is a constant. And if you add that to this equation, so add them together, you get 2f and then plus g minus g, so that's 0, is equal to little f plus a constant. And, well, okay, let's just write it all out. So f is equal to 1/2 f plus some other constant. Well, let's just write constant divided by 2, whatever. And so then you plug that in to say here. And you find that g is equal to f minus that constant. So that's 1/2 little f minus that constant over 2. Anyways, the point is, if you look at the sum of them, the constants cancel out. So there's no, you don't need to, so there's no need for the constant and all this business. Because for any value of the constant, you get the same solution u. Because remember, u is the sum of these two functions. And so on one of them, you have a positive constant over 2. On the other one, you have a minus constant over 2. When you add them together, they cancel out. So it's always going to give you the same solution to the equation. So there's no need for the constant. And so f of x is equal to 1/2 f of x. And g of x is the same thing, 1/2 f of x. But remember, when you actually form the solution to the wave equation, you plug in different things into these functions. So it's not like they're the same function of one variable, but they do different things for the solution. Right. Now, this is, let's be careful. What was this whole logic for? This was for, this is when x is in between 0 and L. This is when x is in between 0 and L. Now, so whenever you plug in a number in between 0 and L into f or g, you will just need to compute 1/2 f of x, if x is in between 0 and L. But, so okay, so that's what we've determined so far. We're only plugging in numbers into f and g in between 0 and L. This is the important and confusing part. But we want to plug in numbers into f and g that are bigger than L or less than 0, because we're not only plugging x into f and g, we're plugging in x plus time, and time is unbounded. X is bounded in between 0 and L, but t is unbounded. So, you know, if t is 1,000,000, you want to know what f of x plus 1,000,000 is, which we have no idea right now, because we only know what f of x is when x is in between 0 and L. So anyway, so we only know, we haven't figured out everything about f and g yet. We've only figured out that the capital F and capital G are equal to 1/2 little f when you're plugging in a number in between 0 and L into the big f and g's. So big, that's the confusing part. But now we need to figure out, so, you know, well, I think I say this in the next slide. Right, so both the f and g are just 1/2 little f, the initial displacement, when x is in between 0 and L. But you got to plug in all sorts of numbers into f and g, not just numbers in between 0 and L. So what is, you know, f of 3/2 L, for instance? We don't know yet. I meant capital. Okay, but we have not taken into consideration one of the boundary conditions yet, the spatial boundary conditions. There needs to be 0 at either endpoint. So that's the thing that's going to sort this out. Yeah. Okay, so I say a lot there. So let me just, before we read that together, let's just take a look. Okay, so we have the boundary condition x of 0 for all time needs to be 0. Let's write that down in terms of f and g. So that tells us f of plus t plus g of minus t, I'm plugging in 0 in for x, needs to be 0. Okay. And u at L t needs to be 0. So f of L, okay, well, let's continue. Well, okay, let's write it down. F plus t plus g of L minus t equals 0. Okay, so what do we do on the left here? Now, we know that the derivatives of these, the derivative of f should be equal to the derivative of g, so we know that f and g should be the same. So what does that tell us? So it says that f of t should be equal to, so let's just think about capital F and not think about g anymore. So this should be equal to minus g of minus t. So okay, that's, but we know f and g should be the same. So this is equal to minus f of minus t. So this says that f needs to be odd. That's exactly what this equation says. F of t is equal to minus f of minus t. That's exactly what it means to be an odd function. Okay, so we know what f needs to look like on the interval 0. So okay, just to fill in the number line so far. So here's 0, here's L, say here's minus L. Let's maybe extend the number line a little bit further than that. Here's 2L, say. Here's minus 2L. Okay, so here's what we just figured out. Okay, so well, I mean, before what we just figured out, we know what f and subsequently g need to be in between 0 and L. Right, that just came from the initial conditions. Now we also know that it needs to be odd. So we know here. So no f here, and then we just need to make an odd extension of it. But we know this function is going to be defined for all numbers eventually. So we also want to know what's going on for all numbers. But because we know it needs to be odd, we know it's going to be we know its value over here. So by oddness, we know what f needs to be here. It needs to be minus f of negative whatever number I'm plugging in between minus L and 0. So let me just clarify that. So in other words, if x, let me use a different letter so to not confuse x with what it represents. If, say, c is in minus L to 0, then a priori I don't know what it is, but I know, by the oddness, I know that f of c needs to be equal to minus f of minus c. And now minus c is in between 0 and L, because c was in between minus L and 0. Minus of it is in between 0 and positive L. And so that is just minus 1/2 little f of minus c. So that tells me what capital F is on that negative little chunk. That's why I just colored it in. We know what it needs to be there. Okay, so, all right, I have another little chunk of the domain where capital F is defined. Now let's see what is going on elsewhere. Well, there's only one thing left to look at, is what's on the right-hand side of the page here. Okay, so I know when I plug in L for any time, I'm supposed to get 0, so that tells me this. Okay, so that tells me F of L plus T is equal to minus F of L minus T. But I know L plus T, but I know it's odd. So let's use that property. So this is my oddness of F. Minus F of this thing is equal to F of minus whatever's inside, T minus L. Okay, so when I take F of T and I add L to it, okay, let me, if you rewrite this, you think of T as L plus Xc. So okay, let's think. Xc is L plus T. Then this equation reads as F of Xc is equal to F of T minus L. Wait, no, that's not right. Oh, yeah, it looks like Xc plus 2, whoops. Looks like Xc plus 2L. Okay, if you solve for what? So T is Xc minus L, or sorry, minus 2L. It's not important if it's plus or minus. The point is it is 2L periodic. So it implies 2L periodic. If I subtract off 2L from whatever value I am now, I get the same thing. So every 2L needs to repeat. That's what we just learned. Therefore, okay, I know it on so I know this function on an interval of size 2L, and it's 2L periodic. That's the end of the game. You know exactly what F needs to be. It's just going to repeat itself. So whatever it is from minus L to L, I just need to subtract 2L from any other, if I want to evaluate any other portion, I just need to subtract an appropriate number of 2L's in order for the unknown number minus that copy of 2L's to lie within negative L to L and evaluate little 1/2 little f there. Okay, so that's a mouthful. Why did we just learn? So here's a summary of what just happened. Okay, so the boundary conditions imply that f is odd. So whatever's going on from 0 to L, it has to be doing kind of the double flip of that on minus L to 0. And it needs to be 2 pi periodic. So you could say that it's equal to 1/2 f sub OP, where OP is what you get by extending f to be an odd function. So f is just a function from 0 to L. Extend that to be an odd function on minus L to L, just by defining. So the odd extension of f and x is just f of x if x is in between 0 and L, is minus f of minus x if x is in between minus L and 0, as I described earlier. Okay, so that's what is meant by the odd extension of f. That's not defined from minus L to L. And then you extend this function to all numbers by just making it periodic. So, so for example, well, f of f sub OP of x is equal to f is equal to the odd extension of f at x, at x minus 2L if x are 2L times k, if x is in the interval 2k minus 1 L to 2k plus 1 L. So if x is in that interval for a whole number for k, whole number k. So if x is in that interval, then you have to shift it appropriately, subtracting off from x to lk, and then plug that number in to the odd extension of f. A picture might be useful. So if f looks like this, from 0 to L, then the odd extension of f would look like this. So let's see, here's L, here's 2L minus 2L. Then it would look like this. Okay, look like a little bump there, a little bump in the negative direction there, and then you repeat that. Negative bump there, positive bump here, positive bump there, negative bump there, etc. Periodic extension of f. That is what f is, and g is the same thing. So what did we just find? Putting it together, here's what we get. The solution to this is the confusing. This odd periodic extension is the confusing thing, but now we've worked it out, and we can conclude that the solution to the wave equation using the D'Alembert form, this idea that D'Alembert gave us, will just be 1/2 the sum of two things: odd periodic function evaluated at x plus t plus odd periodic function evaluated at x minus t, different numbers. And their sum, their average is the displacement of the string at some point xt. Okay, very good. Okay, here's a kind of a silly example, and actually the one that we talked about earlier. But here's something I could ask you. Find the solution to the wave equation on the interval 0 to 1 with c is equal to 0. Or sorry, c is equal to 1. I didn't mention that, but I meant it. With the Dirichlet 0 boundary conditions and some initial condition sine of 4 pi x. Okay, so we have sine of 4 pi x on 0 to L, or 0 to 1. Okay, so that is going to oscillate twice. That is what f looks like. That's the initial displacement, 0 initial velocity, and you let the wave equation do its thing. Okay, well, what did we just find from D'Alembert's solution? So we just found that this is going to be the solution, u of xt, the displacement of the string at point x time t, going to be equal to 1/2 f of the odd periodic extension of f at x plus t plus the odd periodic extension of f at x minus t. Okay, notice what's the odd extension of sine? Well, it's sine. And then you want to make that periodic. Well, the periodic extension of sine on the interval is going to be sine, but just it's formally different because it's like this sine function f is formally only defined between 0 and 1 to make it periodic. Then it's defined from the interval -1 to 1. The definition is just sine of 4 pi x. So the formula is going to be the same, just formally it's a different function because it's defined in a larger set. Yeah, I made this a little bit, it's kind of silly because you don't have to think too hard. Or maybe if you think too hard, you get extra confused, and that's not good because of that. But otherwise, things get overwhelming and writing down. You know, the best way to describe the odd periodic extension of a function is just that, in those words. If you want to write down a formula for it, it's going to be cumbersome. But anyways, so the odd periodic extension of sine of 4 pi x, or x in between 0 and 1, is f of t. Say if c is sine of 4 pi x. I mean, the way you can see that, so the odd periodic extension, it's a unique thing of a function. So you can just check, is this going to be an odd periodic extension? Well, first of all, is it an extension of sine of 4 pi x? Yeah, it has the same form of sine of 4 pi x on 0 to 1. It's literally the same formula. Is it odd? Yeah, sine is an odd function. Is it periodic? Period 2. The answer is yeah, it is periodic with period 2. And period is even smaller than that, but it is definitely 2 periodic. Anyway, so this is the odd periodic extension. Okay, so what do we get? So this is 1/2 sine 4 pi x plus t plus sine of 4 pi x minus t. Okay, you know, so recall. Okay, let's write this down more simply, and also touch base with the. So we actually solved this problem before. I didn't say what the initial conditions were exactly, but we solved this problem before. You know, that was the example I worked out, that product of sine and cosine function that I worked out earlier on in the lecture. Well, it's just, so this should be the same thing, because there should be a unique solution to the wave equation, because we specified the right number of initial conditions. We should get the same formula. Doesn't look exactly the same now, but recall that sine of, you know, alpha plus or minus beta, you can write that as like sine alpha cosine beta plus minus sine beta cosine alpha. And you find that when you do that formula to both of these two little expressions here, you will get some cancellation, and what you get in the end is sine of 4 pi x times cosine of 4 pi t. If you use that trig identity, which is the same as before. That's the same formula that I wrote down earlier. And the picture of the solution is, yeah, it just looks like the sine function, but it like goes down to 0, and then it becomes like negative of the sine function, then it squishes down to 0, and then it becomes positive of that sine function. And that's what happens. Again, it looks a little bit unnatural. But let's take a okay. So we've worked that example out. That's an example of a. I could ask you that question on the exam. You would be somewhat happy to see that question, because figuring out the odd periodic extension of that thing is not so hard. Okay, but just to give you a greater feel for the wave equation, because so far we just haven't seen, we just saw this like little kind of toy, this kind of like elemental piece of wave motion, which doesn't really feel like wave motion. And then we saw like the translating wave. So let me share with you, you know, we can write down solutions pretty easily, but it's kind of awful in terms of piecewise defined functions, because when you do the odd periodic thing, it's, anyways, but you can get a very nice pictures of these solutions using the Dolbear method, or just the semi-numerical method. You get very nice pictures. Let me show you an example of one on a YouTube video I found. Surprisingly hard to find. Well, never mind that. Maybe it's not that hard, but all right. I didn't find it. Okay, so here's a little. I didn't make this, someone else did. This is the initial condition here, and I think there are 0 is the initial displacement, and then no initial velocity, and then the heat equation, or sorry, the wave equation runs. So what would you expect? You would expect this to kind of break into 2 pieces, move to the sides, and then kind of, well, you'll see what happens. Here we go. Oh no. Okay, but you see it bounces off the sides. The Dirichlet conditions has the effect of making the waves kind of bounce off the walls. And that's what, when we form the odd periodic extension of those functions, and then you do the you know, x plus t and the x minus t, you plug it into odd periodic functions, that's the effect of that. Not obvious that that's what's going to happen, but that's the effect. You have this, you kind of can see, okay, the translating is because you're adding the, as time goes on, you're shifting the function to the right. As time goes on, that's the effect of adding t in there. And then the fact that it's the odd extension makes it kind of go from plus to negative when it bounces off the wall, or you know, the sides when you pin them down. Okay, very good. So that is what I wanted to tell you in this first part of the final lecture. All right, there's going to be a second part uploaded separately on the final 2 sections that we'll cover, and I'll see you there soon.